still in no rush to even crack the book open and look at chapter 1, because I've taken a look at chapter 1, and I think we need to know a little bit more before we go. Okay, so the first half of the book is about the atmosphere. So we need to know about gases. We need to remind ourselves about gases and mixtures, because two components occupying the same space, when the interactions between gases are so small and they occupy so much space, and the space between the particles is so large, we need to talk about mixture behavior. And then they open the book with ozone, and ozone does something really clever by absorbing and then using ultraviolet energy. And it does a reaction, and a reaction turns this covalent molecule into another covalent molecule. So I think we need to revisit what it is to be a covalent molecule and a little bit about bonding. Nothing too complicated, just chemistry 1 stuff. But then the interesting part, the chemistry part about the ozone layer is has been studied really well in terms of kinetics. Kinetics is a chemistry 2 topic, and is about the speed at which reactions work. So let's, before we open and talk about, here's the ozone absorbing ultraviolet, doing a potentially radical mechanism where there's multiple steps, and the rate determining step is not the first step, so it doesn't follow simple mathematical models. Yeah, everyone's going to get up and turn around and leave the room. So we are not in a position to talk about that. All right, so the atmosphere is a mixture of gases. We just free-formed a whole bunch of stuff on the board on day 1, and one of the topics that came out was contamination. Contamination gives us the sense of purity. Okay, so I'm going to get to mixtures by thinking about purity. What exactly does it mean to be pure, and what exactly does it mean to be contaminated? To be contaminated, can you be a mixture of things and still be pure?
No.
Okay, so if I had a bottle of red marbles, and I had a bottle of blue marbles, and they were completely separate, I would have one sample that is pure red marbles. And there's a market somewhere for pure red marbles, and there's a market somewhere for pure blue marbles. What if I stuck them together in an exactly 1-to-1 ratio and sold them as a mixture of blue and red marbles? Would it still be pure? Yeah, I mean, some of these questions.
Philosophically,
yeah,
yes,
so
it's technically a pure mixture of red and blue marbles.
This class will have the most amount of potentially philosophical questions, because there are so many factors at play that this is not going to be hard science. Okay, so if I was a scuba supplier, and I give you a scuba tank, and I tell you, don't worry, everything inside the tank is pure. What's inside the tank?
It's a
avoid the nitrogen. There's going to be nitrogen in there and oxygen
Yeah.
because it's compressed air. It's not pure oxygen. That would be too expensive, is the reason why it's not pure oxygen. And dangerous, we can't inhale pure oxygen. We have to, our metabolism isn't ready.
So if it's, I mean, I guess that's how I would look at it would be if they list the gas mixture in the tank,
Yeah,
then as long as everything that is stated on the tank,
yes.
ingredients or whatever, is only in the tank,
Yes.
and that is a pure mixture.
Then it can still technically pass, probably legally, there'll be a lawyer somewhere will say, well, this is pure. It might not be the definition that we want strictly from the textbook
Mhm.
of pure only contains one thing. But sure. So yeah, scuba tanks contain compressed air, oxygen, nitrogen, and then we throw some helium in. And the helium serves a purpose to get into your bloodstream so the nitrogen in your bloodstream is under those compressed pressures can be problematic because we have no metabolism for it. We can metabolize dissolved oxygen in our blood, we cannot metabolize dissolved nitrogen in our blood. And when you decompress from a depth, you get the bends. You get
yeah.
bubbles of nitrogen gas forming in your bloodstream, and it's apparently very dangerous. Okay, what about a bottle that contains aspirin? When is the aspirin in the bottle pure?
When it's dissolved.
Okay.
Hmm.
Yeah. So to be pure aspirin, which is acetylsalicylic acid,
Yeah.
Or
it would need to be a bottle that contains only acetylsalicylic acid.
Right, but the bottle comes, it has a little seal pack on it,
Yeah.
and it usually comes with like a little pack inside it, right?
And then the pills
And the pill is,
are mostly chalk.
well, I was gonna say that's heavy coating, right? It's all coated in
Mhm.
chalk, so no, it's not pure,
Yeah.
there's nothing pure about it.
But would you accept the purity of an aspirin tablet? Yeah.
In a non-chemistry.
Yeah. In fact, the label will tell you, because there are pharmaceutical rules in the marketplace of you're not allowed to sell me 70% aspirin. It has to be 99.85% pure. Pure from at the moment we manufacture the ingredient that we're talking about. It's not contaminated more than a fraction of a percent at that point. And then we mix it up with all the other stuff, the binding agents and the chalk. Because I only need a granule of aspirin in order to beat my headache. But I can't pick a granule up with my arthritic hands. So I can't take the pill to help my arthritis if I can't pick it up because it's so small. So we pack it in calcium carbonate or something else, or even buffer it now. So that its pills are just the right size that you can handle them and swallow them.
Mm-hmm.
Okay, so purity's not the straightforward thing that we thought it is. It's very, very clear cut at the hard end of science, but in the marketplace, purity is whatever the marketing people tell you it is. Okay?
Whatever the FDA or USDA
Mm.
allows it to be.
Okay. So, in the world, starting at the very, very pinnacle of science, and we're going to work our way down to what's acceptable for the general public. What's the purest thing that there can be? What's the pinnacle of what it means to be pure? We're going to start top of the board is pure, and then we're going to kind of tree our way, fork our way down. That some things can still be pure, but less pure than the things all the way at the top.
So, oh, like the proton NMR? Like, don't
Okay.
we mess around with like hydrogen, hydrogen 3, right? Or wait,
Okay,
right?
so I think I know what you're saying. So that
It's an element. The element
it's
is-
an element.
There you go, thank
Okay.
you.
And in fact, you've gone one more than I was expecting, because you're about to say isotope.
Yeah,
Okay, because elements themselves typically are mixtures of multiple different isotopes.
Mhm.
Some isotopes are trace amounts, and so the atomic number the atomic mass that's on the periodic table is pretty much close to being a whole number. And other times it's not. Okay. Boron has a 10 and an 11. Chlorine has a 35 and a 37. Hydrogen has a 1 and a 2 and a 3, but the 2 and the 3 are very, very small amounts.
It's like
Deuterium and
0.1%.
tritium.
0.1%
Really small, really small. Okay, so right at the pinnacle of what it means to be pure, we have elements. What does it mean to be an element? What's our definition of what an element is?
Yeah, I know. It's the, well, it's like the, I'm trying to figure out the right way to say
Okay.
it. Category, like your category.
Okay, so atoms are small, yes? Yeah. Okay. Matter consists of atoms. If I had a lump this big of carbon, and that carbon was pure, what would be in the lump?
Mostly carbon-12.
Exclusively carbon atoms. And then I'm going to add onto this, because I wasn't mentally prepared for isotopes today, but then also isotopes are a subset of elements that we could say, well, I'm not just accepting any number of neutrons, I'm going to accept only this number of neutrons. So even purer than an element would be an isotope of that element. Okay, elements we can define as they contain only one kind of atom.
That's like the hardest definition I've had in a while. It's embarrassing.
Isotopes are types of elements where elements can exist in more than one, I don't want to say form, because I don't want to give you the impression that adding an extra neutron to carbon makes it not be a solid anymore. It's not like it, not in a different state, but they, sure.
I mean, ish.
So an isotope contains a specific ratio of protons and neutrons. Okay. So the three subatomic particles, I don't think we're going to really have to talk about subatomic particles a lot. There's a late chapter on radioactivity, and radioactive contamination is a thing, so we might visit atomic structure at the end, but you'll remember from chemistry 1, atoms are our smallest indivisible particle. In the purest state, atoms exist as elements. Hydrogen is its own element, carbon is its own element, nitrogen is its own element, protactinium is its own element, They have their own space on the periodic table of elements, and they have their own particular number of protons. Protons are the positive charged subatomic particles that live in the nucleus of the atom. That's the speck that's at the center of the atom. Most of the atom is empty space, where the electrons have orbitals around the central nucleus. Protons are positively charged, and neutrons are about the same size and mass, tiny little bit different than protons, and they both live in the nucleus. Electrons are the negatively charged particles that exist as a wave function. We pretend that they're moving particles because it's easy for people to comprehend. Planets in orbit of a sun, moons in orbit of a planet, we kind of pretend that they are moving point charges, because the truth is very, very complicated. And because protons are positives and electrons are negative, the number of protons and the number of electrons have to be the same. So the ratio that we're talking about for isotopes is dictated by the number of protons to neutrons. The number of electrons is always the same as the number of protons. I could write it on the board, but it's unnecessary. Okay? So the number of protons for any particular named atom is fixed. Carbon has 6 protons. So it's position number 6 on the periodic table. Hydrogen has 1 proton. It is position number 1 on the periodic table. But the atomic mass of an element is dictated by these 2 numbers. Electrons are incredibly light. You need about 2,000 of them. You need 1,836 electrons to equal the mass of 1 neutron. Okay.
I didn't know it was that big.
Yeah.
That was that much.
So when you're counting the mass of an atom, we don't bother counting the electrons. You just need to count the mass of the protons and the neutrons. Okay? So adding a neutron, which has mass but no charge, so it doesn't contribute to the chemistry or the physical behavior of the atom, other than make it heavier. When you make the atoms heavier, physically they'll behave differently. Chemically they'll behave the same way. When we change this ratio, the atoms still contain their identity. Okay? So we have things like that pen does not work at all. Carbon-12, if we count the number of protons, neutrons, and electrons, the number of protons is given by the atomic number. The number of electrons is dictated by the number of protons. Electrons are negative, protons are positive. If I have 6 positives, I have to have 6 negatives. And then the number of neutrons is the gap between these 2 numbers. This is the mass number, that's the atomic number. This tells us how many protons in it there are. This tells us the combined number of protons and neutrons. There you go. Well, there is an isotope of carbon called carbon-13. It's still a carbon, so it still has 6 protons. It's still a carbon, so it has 6 electrons, but now it has 7 neutrons. Years from now, when people watch the YouTube video, they won't know what that means. But the difference between 13 and 6 is now 7. And so we have 7 neutrons. Okay. And because this is more specific, I'm not just telling you carbon, I'm telling you carbon-13. That's an extra layer of purity on top of what we were already thinking. So the pinnacle of what things can be is that they could be elements, or specifically isotopes of a given element. Okay. If I had a sample of carbon, which is just on the board, and I sprinkled in some lithium, then nothing's pure anymore. We now have a mixture. Okay? So, this is the single entity. There's only one thing in an element or an isotope of an element. I'm just going to branch, and I'm going to make two things occupy the same space, one of which is going to be contaminated, and one of which is still going to be pure. Because that's possible. If I take a bottle that contains hydrogen gas, and I take a bottle that contains oxygen gas, and I mix those two gases together, now I have a bottle that contains hydrogen gas and oxygen gas in the same container, occupying the same space. That makes that a mixture. If there was a spark, then the hydrogen and the oxygen would combine together to make water. There are two words at play in chemistry that feel like they're interchangeable. They're not, but we're not going to yell at anybody for getting these wrong. Compounds belong to things that will belong in the world of ionics. Molecules belong to the world of covalent. Actually, before we even get to this, because we're going to start talking about ionic, there is another sub-branch. It belongs right here. Before I mix them together, we can classify elements. You can classify elements. Elements belong to two categories. 3 if you go, are you a solid, liquid, or a gas? If you go, are you solid, liquid, or gas, then that's a subcategory that we can divide things into. Most of them are solids. Bromine and mercury are liquids, and then a handful of them are gases. Hydrogen, nitrogen, helium, argon, neon. But elements themselves, I'm going to write this on either side of the branched arrow. Elements themselves can be classified as metals or not metals. The world is quite clear about this, that as an element, you are one of the other. It's a little bit more gray than that. In organic chemistry, the gray area is worth investigating. In the semiconductor world, where we have metalloids, that non-metals don't conduct electricity, metals do conduct electricity, and there's a little bit of a gray area on the periodic table where you're neither a metal nor a non-metal, or you're a little bit of both, and you end up being a semiconductor, things like silicon. And we can mimic silicon's behavior by mixing elements on either side of that. So like gallium arsenide kind of combines together to be in that middle range. Okay, but clear demarcation. You're either a metal or you're not a metal. We did this on day 1 of chemistry 1. Metal or non-metal?
From the right side?
Oh, yeah,
Oh.
it's metal.
How do you know?
The sound.
Yeah, I said sound.
Metals make a pinging sound when you hit them, and they are cold to the touch because they conduct heat and they conduct electricity. If we've invented electricity, we understand that they conduct electricity, and they can be molded and hammered into shapes, and they taste a particular way. You're not allowed to taste them anymore. And if your material that is pure and is an element does not make a pinging sound when you hit it, and does not conduct electricity, and does not conduct heat, and cannot be hammered into shapes, and cannot be extruded into wires, then you do not have any of the behavior that makes you be a metal, and you are a non-metal. And on a periodic table of 120 elements, 100 of them are metals. And only the small, far right end of the periodic table gets to be a non-metal. Okay. Now that we've said metals and non-metals exist, we can put combinations of these together, and we're either going to make compounds or we're going to make molecules. Compounds contain metals and non-metals. Things from the left-hand side and the right-hand side of the periodic table. The very beginner level of our understanding of this, that everybody kind of goes, oh, well, I know what salt is. Sodium chloride is salt. Sodium is on the very, very far left of the periodic table. It is definitely a metal. Chlorine is on the very far right of the periodic table. It is definitely a non-metal. This is a metallic solid. That is a non-metallic gas. You put them together and you make a white crystalline solid. The salt that you sprinkle on your fried chicken strips from the commuter lunch today, was the salt pure?
Yeah, we don't know.
Yeah.
Really?
It is staying on the left-hand side of this board. Pure stuff is going to be at the top and the left. I mean, I haven't written it yet, but that's how I'm envisioning this going to go. And then the contaminated mixture, messy part is going to be here on the right and down at the bottom. Sure, sodium chloride can be pure. It is billions upon billions of ions of sodium and chloride in a 3-dimensional lattice that extends just like massive repeating structural units of the same thing. And if there's an impurity in there, then the crystal doesn't grow right. So if you can grow a crystal of it, it's mostly pure. Good enough to be good enough for us. Elements can grow crystals too. Carbon makes diamond. Diamond is one of the allotropes of an element. An allotrope is the outward expression to the world of how an element exists. So carbon gives us graphite in your pencils, but also diamond. In organic chemistry, what happens if we throw an impurity into the diamond? It's not pure anymore. And it depends what the impurity is. If I sprinkle in like 1 ion of cobalt every now and then, you get this intense color. You get color sensors inside things. So yeah, there can be impurities that are encapsulated in. You'll have learned about Schottky defects and Frenkel defects. We're not doing any of that in this class, don't worry about it. So we can have pure material that is combinations of other things. Okay?
Sorry, did you see the shrimp that grew out of the woman's bag of sea salt she had?
No. She'll have to.
I'll have to show you the video. after.
Actually, a headline came in last night that I pulled and to put it to my email, I will send it to you.
Yeah.
It's potentially a talking point. Microplastics.
Okay.
Talking about microplastics day
Yeah.
one. The Guardian, which is a respected newspaper out of England, just published that somebody's scientific findings think that microplastics are wildly overestimated. That what people are finding as microplastics in the samples that they're looking at are actually the microplastics that are in the lab and on the people who are doing the investigation and in the method that it's collected. And that the microplastics that are out there in biology might not be what we think they are. It's worth a look.
Yeah.
You know how this goes? Sometimes it swings wildly one way, it gets refuted for a minute. Cholesterol exists. There are 2 types of cholesterol. One of them's really bad, and the other one is good.
And then,
For a decade.
and then
No,
the
it's the
ratio.
other way around.
Now it's the ratio.
Yeah, it was high density cholesterol is bad for you, low density cholesterol is good for you, and then a decade later, listen up, we've changed our mind. It's the other way around. Yeah. So stuff happens, but I saw that
Really
headline
interesting.
come
That's
in
really
yesterday, and it's something that we'll pull up and read
Yeah.
in class. Okay, molecules are what happens when you have bonding between just the non-metals. So the non-metal part of the world that's really interesting is the carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur part that gives us biochemistry. These are all the non-metals. The bit that has chlorine and bromine and fluorine in it, those are also non-metals, but they're not really biologically relevant. When you stick a chlorine into a biomolecule, it tends to become like antiseptic, which is great because you can kill germs. But then what are you going to do with it at the end of the day when you have to wash it down the sink? Because it kills all the germs in the sink. Well, that's great. We want all the germs in the sink to be dead.
And then the water treatment.
But then it kills the germs that are in the stream, in the soil. The germs, the little microbes that these slightly larger microbes live on, that the insects live on those ones, and then the birds live on those insects, and then the hawks live on those. And so we get a chain effect of when we kill the little tiny things, which we're all happy about, there's a knock-on effect somewhere. So something like water. Or any of the like hydrocarbons that we do in organic chemistry of like, oh, gasoline. Gasoline is octane. It's a completely natural covalent molecule. We don't think of it as being natural because it's hidden from us in our environment. Our environment is only what we experience. The world where the hydrocarbons is underground, so it's not in our experience of what the environment is. And so when what was underground leaks into what is on the surface, or what we can feel, we feel like, oh no, that's now contamination. Okay, these can both be pure. They are combinations of elements. We want to be sure not to say they are mixtures of elements, because a mixture means occupying the same space but no chemical interaction. Compounds and molecules have a chemical interaction. The interaction that happens in compounds is what we call ionic. Metals on the left-hand side of the periodic table undergo a very small change and become positively charged. We call a charged atom an ion. Positively charged ions are called cations. And they get to be positive because the piece of information that we had up here, protons are positive, neutrons have no charge, electrons are negative. If we dislodge electrons, which are very easy to dislodge, one of the experiments we're going to do in physical chemistry lab, maybe not next week but the week after, is we're going to dislodge some electrons from some atoms, and then we're going to measure their charge. They're on the outside. They're the easiest things they were the first subatomic particle to be discovered because they are the easiest to dislodge. They're the easiest to observe. So if I knock an electron off an atom, now this balance between positives and negatives doesn't exist anymore, and the metal has more protons than it has electrons, it adopts a positive charge. The electron that we lose from the left-hand side of the periodic table travels over to the atom on the right-hand side of the periodic table, the non-metal, and is picked up. This loss of electrons has a name in chemistry. It's called oxidation, and the gain of electrons is called reduction. In this class, there is probably a point in time where there's definitely a point in time where we're going to look at cycles, or like the nitrogen cycle, and we're going to say these are the oxidation states of nitrogen as it goes from one place to the other in the environment. Oxidation is the loss of electrons. In the simplest case, and we'll do this when we look at the actual scheme, in the simplest case, we don't need to follow the exact number of electrons. We can look at how many oxygens are you capable of being bonded to, and that will give us a guide. Okay? Oxidized, positively charged ion, reduced, negatively charged ion. Positives and negatives attract each other. So these two are now stuck together. And then there's another sodium here, and then there's another chloride, and then there's another sodium, and then there's another chloride, and then there's another sodium, and then there's another chloride. And that's just in this dimension. There's also, in front of the sodium, there's another chloride, and then in front of that, there's another sodium. In 3 dimensions, forever. billions and billions of them in a grain of crystal. By the time you've got a lump of salts, it's got numbers of repeating ions that are too large for the human brain to comprehend. Okay. Now, ionic behavior, different. What we're going to do for ionic is we're going to count where you are on the periodic table, and we're going to blend the electrons together until we get to 8. And at 8, we're going to stop. 8's a magic number in chemistry. We're just going to stop and say you've done enough, you've made enough bonds. Okay, so this is the world of covalent chemistry. And a covalent bond, the ionic bond is just the attraction between the positive and the negative. A covalent bond is 2 electrons shared between 2 atoms. Okay? So if we look at the periodic table is organized in vertical columns that are called groups. Those groups are assigned numbers. There are 8 vertical columns that go all the way from the top to all the way to the bottom. There's a bunch in the middle that are only at the bottom. We're not going to worry about them. In group 1, I have hydrogen. In group 2 and 3, I've got metals. I've got beryllium and magnesium and calcium. In fact, in group 1, I've got the sodiums and the lithiums here. But hydrogen gets to be a non-metal. The others are metals. And we've said that if you've got a metal, you get to do this type of chemistry. It's only the non-metals that do covalent. So the only thing on the entire left-hand side of the periodic table that I'm even going to consider is hydrogen. Hydrogen is here, carbon is there, nitrogen is here, oxygen is there, and fluorine is here. Let's go to fluorine. Okay, the numbers tell us the numbers of electrons. The group numbers on the periodic table represent the number of electrons that the atom displays to the world on the outside. Hydrogen has 1 electron. We show that electron as a dot. Carbon has 4. 1, 2, 3, 4. Put them as far apart from each other as you can possibly go. Nitrogen has 1, 2, 3, 4. Put them as far apart as they can go. And then you come around. And so this one up here, this is the first time that we see something new. Carbon just has 4 electrons. And electrons are going to be shared in these things called covalent bonds. Nitrogen has already paired 2 of its electrons up into what's called a non-bonding pair of electrons or a lone pair of electrons. They are not available for bonding. We cannot make bonds with those. And then when we get to 6, 1, 2, 3, 4, 5, 6, oxygen does the same thing. It has 6 total electrons. 1, 2, 3, 4, 5, 6. I now have 2 lone pairs of electrons. That's 4 electrons that are not going to be making bonds under this description, because it's shared between 2 atoms. So I'm going to share that unpaired electron with another atom down here. I'm going to share that unpaired electron with another atom over on the side. Fluorine in group 7, I'm running out of space, goes 1, 2, 3, 4, 5, 6, 7. It means that most of the electrons in the fluorine are not interested in making any kind of bond at all. Just the one. Only that electron right there. if I keep going, I get to neon, which is 1, 2, 3, 4, 5, 6, 7, 8. 8 gets to be our magic number. Neon already has 8 valence electrons. It has no interest in getting any more. It has no interest in losing any of the electrons that it has. This exists in nature as an atom. Nitrogen and helium and argon that are in group 8 exist in nature just as atoms floating about because they're gases. Fluorine is always going to be in combination with something because it has 1 electron that it wants to bond so that it can have 8 electrons. All right, let's pick this oxygen out because we've already got water on the board. There's a hydrogen with 1 electron. Here's an oxygen with 6. If I go 1, 2, 3, 4, 5, 6, this oxygen can share this electron with something and can share that electron with something. If I bring along a hydrogen, I just made a covalent bond. This is 2 electrons shared between 2 atoms. This is 2 electrons shared between 2 atoms. This is how the world of covalent bond works. It's only between non-metals. It's a much more limited possibility because it has to only come from a very small number of elements, and yet this is going to give us all of protein, all amino acids, all your DNA, all your fat, all your sugars, carbohydrates, all biomolecules out of here. Minerals here. Covalent biochemistry here. Okay. Let's put those 2 things together. I have salt and I have water. What if they're in the same container? You're thinking at a slightly higher level than I need you to right now.
It's going to dissolve the salt.
Yeah, the salt and the water will occupy the same space and become a mixture. In fact, they're a special kind of a mixture called a solution. So, mixtures. Mixtures are 2 or more components that occupy the same space, but most definitely not interacting chemically. How do we know? How do we know that they're not interacting chemically? If I put the salt and the water together, the salt would look like a brick. I could have a big chunk of salt and then I have a bucket of water and I put the brick of salt in the bucket of water and I go away, and when I come back, the brick of salt has disappeared. Did somebody come along and take it out of the bucket? I'm not sure. It's not there anymore. It has disappeared. It's dissolved. It's become part of a solution. But how do I know that the salt and the water are just occupying the space together and have not done anything chemical? How do I know that?
Because if you evaporate all of the water, you would have just the salt left over.
Yeah. I can separate the components back. The deal about mixtures is that they can always be separated. If I let the water evaporate, the salt would be left behind at the bottom of the bucket and I wouldn't have lost any of it. Every gram of salt that I put into the bucket would still be there if I evaporated or boiled the water off. Okay, now, mixtures can be all sorts of things. We have 3 phases of matter. There's a 4th. There's potentially a 5th and a 6th. But we have 3 that are worth talking about. They are solids, liquids, and gases. Okay. So our 3 phases of matter, or states of matter. Are solids, liquids, and gases. All right, let's see what we can throw at the board and make stick. Can I have a mixture of 2 solids? Is that a thing? Could that be a thing?
Yeah.
Absolutely. Earlier on, blue marbles and red marbles occupying in the same jar. 2 solids. They're not the same as each other, but they are occupying the same space. And if I wanted to separate the blue marbles from the red marbles, I would just pick the red ones out and leave the blue ones behind. If I've got a bowl of sugar and a bowl of sand, and I mix those together into one bigger bowl, is that a mixture?
Yes.
It's a mixture because there's sand and sugar in the bowl, and as long as I leave it, the sand and the sugar do not interact with each other and make something new. They just occupy the same space, but they don't interact chemically. Can I separate the sand from the sugar?
I mean, realistically, no, not yourself, without tools,
Machine.
a machine of, I mean, you'd have to have something. It's almost impossible, but you can. Right?
Sure.
I don't know, no, I guess not,
Okay.
no, wait, yes,
Yeah, I think you can.
yeah.
How?
That's a good question.
How about, so I have a bowl of sugar, I have a bowl of sand, and I have a bucket at my feet. I put both the bowl of sand and sugar into the bucket. Why would I do such a thing? Nobody knows. Some people just want to see the world burn. I have a bucket with sand and sugar in, and I want the sugar to come back out. I want them to be separated. How about I pour a whole bunch of water into the bucket?
Then you can
Because the
dissolve.
water dissolves the sugar, but it doesn't dissolve the sand. Because they are 2 different types of material. The sand is a mineral. And the fact that it's ionic doesn't mean it's soluble in water. Lots of ionic material is soluble in water because water is capable of solvating these charges. But sand is a silicon oxide or an aluminum oxide or a mixture of both and is not soluble in water. Sugar is carbohydrates. It's got lots of OH groups, carbon, oxygen, hydrogen groups, alcohols, dangling off a little ring of carbon. And that group chemically looks similar to this group, and like dissolves like, so the sugar dissolves in water. And then I get a sheet, and I pour the sludge onto the sheet, and the water with the sugar runs through the sheet, and the mud, that is sand and water, stays on the sheet, and now I have sugary water and mud, and I let the sugary water evaporate, and I have separated my solid-solid mixture. They can always be separated. Sometimes it's more of an intellectual exercise. Well, how about this one? I have a mixture of carbon 12 and carbon 13.
Can you separate that?
You can I know you could identify
Yeah.
which carbon is carbon 12 and which carbon is
Yeah.
carbon 13.
Right, say that.
Via the NMR?
NMR.
Yeah,
Yeah.
through the stretching, the
So
carbon
NMR
stretches.
sees this one as being invisible, if you can see something as being invisible, and sees that one as a spin half nucleus. Yeah.
I don't,
What's the difference between these two things?
one more neutral.
Okay, which represents what presents itself to the universe as what?
A radioactive isotope?
Okay, what's the difference?
I mean,
Physically, what is different?
the weight.
Chemically, the weight's different.
The weight.
Okay, if I have a bucket of rocks, you know how rocks go? You have sand, and then gravel,
Mhm.
and then pebbles, and then rocks, and then boulders. What's between a rock and a pebble?
A stone?
Cobble. Yeah, I asked last
Well, for the
year. I
British
asked.
stone, I think it's quite different.
I asked the landscaper to put river rock in at my house because I had soil erosion from the water that just every spring washes my soil away.
Mhm.
And we had all envisaged just, oh look, pebbles. No, with this level of erosion, they gave us cobbles. Cobbles are this big. And that's how before tarmac existed, you would make roads by just putting this roughly the same. It was a skill. It's a skill trade. You'd make the rocks all go together, and they're smooth, and so carts could go over them. Okay, I've got a box of cobbles, the fist-sized, pebbles are smaller, cobbles this big. A fistful of cobbles in the bucket. A fistful of sand. You need more than a fist. A bucket full of sand and a bucket full of cobbles going into a bigger bucket. Separate them.
Oh, you can do it. Yeah, you can do it. So you just have to have some sort of filtration, like,
Shake the bucket.
yeah.
If I throw in a third thing, pebbles. So I've got cobbles, pebbles, and sand. Shake the bucket. The large objects rise to the surface. The small objects fall through the cracks with the agitation and go to the bottom. If you've got holes at the bottom of the bucket, then the small things will come out of the bucket. If you've got pebble-sized holes in the bucket, then the pebbles will come out of the bucket and leave the cobbles behind. They can be organized by gravity. How are we going to separate these two? We're going to organize them by gravity. How? Which tool have you used in the lab that adds gravity to making a separation?
Oh, is it the condensate? It's not the, distillation.
Thinking about a separatory funnel?
Yeah, that's
Well, these are solids.
or, yeah.
But
What's the, I'm trying to think of that.
I'm hinting at the centrifuge.
I was gonna say that, but.
Well, you should have said it.
I'm thinking about liquid.
Well, sure.
Yeah,
Yeah,
centrifuge.
sure,
You understand by
absolutely.
centrifuge, yeah.
Yeah.
By
You
spinning
stick
it,
it
you
in
can
the
get everything.
centrifuge and you spin it, and the most massive particles are going to feel gravitational force or centrifugal force more and go to the end of the test tube. We're not really worried about separating those two, but we are worried about separating these two.
Two different things.
Yeah, these are two isotopes of uranium. This one is the abundant isotope, and it is radioactive. This is a much, much smaller, it's not trace amount, but a smaller percentage of uranium, and it's not radioactive. It's wildly radioactive. So, if I want to build a nuclear reactor, I need this. But I also need this. I need my uranium to be enriched. We call this enriched. If you put more of this in there than is in nature, it's called enrichment. If we take this away from the amount that it normally exists in nature, we call it depleted. You might have heard of depleted uranium and enriched uranium. Now, that's great if I want to build a power station, but I don't. I want to build a device. Device is the government speak for the worst word. There is a worse word, and every time there is a bad word, government says, let's not use that word. I helped somebody a little while ago with a project they were working on for re-entry vehicles.
Re-entry vehicle?
Yeah, re-entry vehicles. My phone is ringing. Well, my phone is also supposed to be recording. We'll call that back. Re-entry vehicle. Re-entry to what? The Earth's atmosphere.
Oh.
Where have you been? The other side of the Earth. What are you doing? You're transporting one thing that used to be here to another place over there, and you had to leave the Earth in order to get there. Yeah. And the device that is in the re-entry vehicle needs to be made out of this, not that. Because this is only radioactive. This is wildly radioactive. I need this. So we put him in a centrifuge and we spin him. And the 238 goes to one end of the tube, and the 235 goes to this end of the tube. It's much, much more complicated than that because they turn them into uranium fluorides, and then the molten, and they spin them, and they build the facilities underground so they can't be seen by satellites. And then Israel and the United States follow.
Yep.
I thought you could only put liquids in centrifuges. I thought you could only put liquids in centrifuges.
Yeah, so they turn the uranium, they make UF6, uranium hexafluoride, which is a liquid, and they put that in the tube and they spin it. And the heavier uranium drags itself to the end of the centrifuge. And the centrifuge isn't, oh look, it's a little test tube. It's
Are they like humans?
big, big thing. Big
Have you
thing.
seen one in person?
No. I've seen the tubes that were seized on a cargo ship that was intercepted leaving, I think it was leaving Rotterdam, and it made a stop in England on its way to an unnamed country in the Middle East for illegal uranium processing plants. They look like, every time you drive down the highway and you see an 18-wheeler with just like giant tubes on the back, it just looks like that. Only they are precision ground. really, really well made. Okay, so solid and solids, yeah. Solids and liquids,
Yeah.
Yeah.
Absolutely.
yeah. Sand and water,
Yeah.
makes mud, mud's a mixture. Salt and water makes, if you become invisible, you are a subset of mixtures called solutions. There's nothing special about a solution other than the fact that the solute, the thing that is getting dissolved, is so finely divided that it cannot be seen by the human eye anymore. How about solids and gases?
Yes.
Can solids and gases be a mixture?
Yes. No.
The answer is mostly no, unless you're defining the volume very, very narrowly. Okay, if we're talking about an open container, if I had a beaker in my hand and the beaker is currently empty. Empty means it's got the atmosphere in there, which is another question altogether. If I pour water into the beaker and fill it halfway up, is the liquid occupying the space? Oh, sorry, solid. We're doing solids. I've got a beaker, and I'm going to fill it halfway up with salt. Is the salt occupying the space with the gas? Salt's at the bottom, gas is at the top. No, it's not really occupying the same space. Unless you really, really want to specify. If we close the container, then we still have to argue the salt is at the bottom and the gas is at the top. They're not really occupying the same container. All right? So I'm going to completely fill the container full of salt and then seal it. And now the gaps between the salt granules have gas. And now the salt and the gas are occupying the same space. So you really have to narrow your definition of what the mixture is in order to make solids and gases be in the same space. Okay? So mostly no. No, we're not going to do that one. What about liquids and liquids?
Yes.
Yeah,
Alcohol and water.
alcohol and water mix completely.
But if you freeze it,
Mm-hmm.
You can freeze alcohol.
no, you can't. But you'll know if it's not
Yeah,
hot
it's
water.
A bottle of water in the fridge will freeze. A bottle of alcohol in the freezer will not freeze. A bottle of water and alcohol in the freezer will freeze. And you can separate them that way, and you can separate them by boiling, because the alcohol will boil off. So liquids and liquids, yeah. Oh, what if it's oil and water?
Can you separate those?
They're already separated,
Yeah.
because the oil floats on top of the water. The question now comes, are you really a mixture? Because are you really occupying the same space? If I have a container and it has oil on the top and water on the bottom, philosophically, are they occupying the same space?
Yes.
Okay. Well,
Philosophically.
no problem then. I say they're occupying this space,
Right.
that space, but they're not occupying this space. No, that space contains only the water. This space contains only the oil. So there's a little bit of, someone will argue with you about some liquid-liquid interactions, okay? The polar and non-polar world separate from each other.
It's like balsamic and all that.
Yeah. Yeah.
You
And
can
sometimes
shake
you
it
can
out.
shake things together and they blend as an emulsion, like,
Yeah. Like a salad dressing.
Yeah.
Oil and vinegar.
eventually they will separate. How about liquids and gases?
Soda.
Yeah, carbon dioxide dissolves in carbonated beverages. Pepsi is full of carbon dioxide. Lakes are not full of dissolved oxygen, but there's enough dissolved oxygen in a lake for the fish to breathe. Not enough for us to breathe. Not enough for dolphins to breathe, but enough for fish to breathe because they have the apparatus for it and we don't. Okay? There's a little bit of physical chemistry in here of that solids dissolve best when they're hot. Solids will dissolve in liquids best when they're hot. Gases will dissolve in liquids best when they're cold. Why you keep your carbonated beverages cold, and why you heat up things on the stove in order to make things dissolve in them. Okay. All right. Well, we're at full time.
Okay.
That is a day one introduction to everything you need to know about everything. I think we'll crack the book.